Greetings and welcome to Distilled. In the previous class, we discussed about certain basic thermodynamic definitions of state properties, path properties. We defined certain thermodynamic variables, and we discussed about thermodynamic equilibrium. We discussed about reversible and irreversible process. So we gave certain basic definitions and basic concepts related to thermodynamics we discussed in the previous class. In this video, we'll be discussing a few more important thermodynamic concepts which are going to be there as you'll be studying thermodynamics. They're going to be there with you throughout. So you need to be very well versed with these concepts while you're dealing with thermodynamics. All right. So first of all, let's understand temperature. All right. So temperature is basically measure of hotness or coldness of a body. Okay, how hot or how cold a body is, you can understand it using the body's temperature. All right. So if I say that I have a particular body A, which is maintained at a temperature of 50 degrees Celsius, while I have another body B, which is, let's say, maintained at a temperature of 100 degrees Celsius. So since this body has a higher temperature, therefore it is going to be hotter. While since this body has a lower temperature, this is going to be cooler. Okay. So that's how you understand the concept of temperature. It's basically the measure of hotness or coldness of a body. The body which appears to be hotter has a higher temperature, and the body which appears cooler has a lower temperature. This is a general phenomenon. Okay, so temperature is measured in degrees Celsius, degree Fahrenheit, and Kelvin. So in the previous few videos, we have somewhere introduced the concepts, the unit conversions with respect to degree Celsius, degree Fahrenheit, and Kelvin. But I'll again mention that. So degrees Celsius, basically Kelvin is the SI unit for temperature. Okay, so to convert degrees Celsius to Kelvin, you simply need to add 273 and you'll get Kelvin over here. Okay, and when we talk about degree Fahrenheit, we convert degree Fahrenheit to degree Celsius. All right, and then that degree Celsius can be converted into Kelvin. So that is some basic conversion that we follow for degree Fahrenheit. So for degree Fahrenheit, we need to use the formula degree Fahrenheit minus 32 upon 180 is equal to degrees Celsius upon 100. Okay, so this is the conversion that you get for degree Fahrenheit. So this is again what we get this conversion using the equation of line. So basically, if we see degree Fahrenheit, so if I plot degree Fahrenheit on the y-axis and I plot degree Celsius on the x-axis, so we know that at, I'll use some other color. So we know that at 0 degrees Celsius, when the temperature is 0, at that temperature, Fahrenheit is 32. Okay, it's 32 degree Fahrenheit. And similarly, at 100 degrees Celsius, at 100 degrees Celsius, the temperature is 212 degree Fahrenheit. So it basically follows a linear relation, somewhat like this. Okay, so let's take any point over here. Okay, let's take any point which has coordinates degree F comma degree C. Okay, let's take any point on this line which have coordinates degree F minus degree C. So we can use the equation of line y minus y1 upon x minus x1 is equal to y2 minus y1 upon x2 minus x1. So over here, your x1, y1 are going to be 0 and 32, while x2, y2 are going to be 100 and 212. So when we use this equation, we are going to get degree Fahrenheit minus y1, that is 32, upon degree Celsius minus x1, that is 0, is equal to y2 212 minus y1 32 upon x2 100 minus x1, that is 0. So from here you will get degree Fahrenheit minus 32 upon 180 is equal to degree Celsius upon 100. So this is the conversion that you need to keep in mind. Okay, so this is how you convert degree Fahrenheit to degree Celsius, and then this degree Celsius you can simply convert it into Kelvin. Okay, so that is how you have temperature. That is a very important parameter while we are dealing with thermodynamics. Okay, once we have dealt with temperature, then let's understand the concept of thermal equilibrium. So remember that if a body appears hotter than the other body, that means it has a higher temperature than the other body. And let's say we bring both the bodies in contact, right? So as you can see over here, this hot body has come in contact with the cold body. So what will happen? Brought in contact with each other, the hotter body, it would transfer some of its heat to the other body. Okay, so now since this is a hotter body, so it is going to transfer its heat to the colder body, the body which is cooler. Okay, so since it is going to transfer its heat, so it will keep on transferring until and unless there is no more heat that can be transferred. Okay, there is no more heat that can be transferred. This situation where no more heat can be transferred, this situation is known as the condition of thermal equilibrium. So under thermal equilibrium, no heat can be transferred. No heat transfer can take place. Okay, that means the temperature at thermal equilibrium, the temperatures are going to be the same, because heat transfer takes place due to temperature difference. It is only and only due to temperature difference. So if there is no temperature difference, then heat transfer will not take place. Okay, keep that in mind. So since no heat transfer can take place, then it would come under thermal equilibrium. Okay, this would be the condition of thermal equilibrium. So as you can see over here, the temperatures of the two bodies have become same. Therefore, no more heat transfer would take place. Okay. Remember, heat transfer won't take place. It is possible that energy might get transferred, but heat transfer won't take place. We'll discuss about this phenomena once you'll understand the concept of heat, work, and all these concepts. We'll talk about this more. But for now, just keep this in mind that while we are dealing with the condition of thermal equilibrium, the temperature of the two bodies becomes same. All right. Therefore, no heat transfer can take place from one body to another. Okay. On the basis of that, we define the zeroth law of thermodynamics. So zeroth law states that if A and B are two individual bodies, let's say I have a body A and I have another individual body B. It's not visible over here. And I have another individual body B. Okay, I have two bodies, A and B. Now, let's say A is individually in thermal equilibrium with the body C. Okay. And at the same time, even B is individually in thermal equilibrium with the body C. So A is in thermal equilibrium with C and B is in thermal equilibrium with C. So the zeroth law implies that this means that even A and B are in thermal equilibrium with each other. So that means if TA is equal to TC, since over here these two are in thermal equilibrium, and over here TB is equal to TC, since these two are in thermal equilibrium, so it can be easily said that even TA is equal to TB, which is actually an implication of the zeroth law. That is what zeroth law states, that if both of them are individually in thermal equilibrium with a third body, then these two are in thermal equilibrium with each other. All right, that is your zeroth law of thermodynamics. It's quite easy, and we are not going to use this law too much, so we'll not be going into the depth of the zeroth law. Now, let's understand the concept of energy. Okay, so energy is basically the capacity of a body to do work. Okay, or energy can be considered as the ability to perform something, right? The ability to perform something. If your body has energy, if your body produces energy, or if your body, if the food in your body that you consume, it gives you energy, then because of that energy, you are able to do the various tasks that you're doing throughout your day, right? So energy is that capacity, okay, of doing work. The SI unit for energy is joule, okay, and in the previous videos we have already discussed that joule can be written as Pascal meter cube, okay. Joule can also be written as Pascal meter cube. All right, so energy is the capacity of doing work. It can neither be created nor be destroyed, but can be transformed from one form to another. This is also known as the law of conservation of energy. Okay, this is going to be a very useful law for us. Law of conservation of energy. It can neither be created nor be destroyed. It can be transformed from one form to another. Okay. Now, it can have various forms, for example, potential energy, kinetic energy, internal energy. So potential energy is basically the energy by virtue of the position of a body. Suppose if a body is situated here at this point, then because of this position at which this body is situated, because of this position, the body might have some energy. Okay, it might have some energy. So that energy is basically the potential energy. Okay, so let's say if this is my ground level and I have situated my body over here. So this body, if it is left free, then it can definitely fall down, right? It can definitely fall down. So it is doing some work, right? It is doing some work. This work it is doing by virtue of the potential energy. Okay, it is doing this work because of this potential energy, right? So potential energy is because of the position. Since it is placed, it is located in such a position, therefore it has some energy in it. Okay, so that energy is the potential energy. Kinetic energy is the energy possessed by a body by virtue of its motion. Okay, so if a body is moving, if a body has a certain velocity, then that body is said to have energy. That energy is known as its kinetic energy. Okay, and internal energy is the energy that is stored within the body. We'll discuss more on internal energy further in this video. But for now, these are the three different forms of energy that we have discussed. There are many more: mechanical energy, thermal energy, right? There are many forms of energy that can be discussed. Okay. Energy is transferred from one body to another. Okay. And it takes place due to some driving force. Okay. The energy transfer, it takes place due to some driving force. Okay. So if I say that this body has some energy A, and I have another body which has I have a body A, I have a body B, and let's say this body A, it transfers some energy E to this body B. So this energy transfer, it is going to take place because of some driving force. Remember, whenever a transfer operation takes place, it is always due to some driving force. Okay, some driving force leads to the transfer operation. For example, let's say this is a hill. Okay, let's say this is a hill, this is a slope, and over here you have an object. Okay, you have an object over here. The transfer of this object from here to here is actually because of the height, right? It is because of the height. So this height difference, the difference in the height is basically your driving force over here. All right, that difference in the height is your driving force. If let's say you have an electrical circuit, right? If you have an electrical circuit and current is moving from this point to this point, right? current transfer, electron movement, electron transfer is taking place. So that is basically due to something called potential difference. So over here, potential difference is going to be your driving force, right? Similarly, if let's say this over here, this body is maintained at temperature Ta and this body is maintained at temperature Tb, then from A to B, heat is going to be transferred, and that is because of temperature difference. Okay, that heat transfer is going to take place because of temperature difference, right? There are many such examples. You can take concentration difference, right? Let's say you have a mixture. You don't have a mixture. Let's say you have you people might have started up about, all right, let's not discuss about complicated topics. Let's say you have a membrane over here, all right, and over here, let's say the concentration is Ca1 and over here the concentration is Ca2. Okay, and Ca2 is greater than Ca1. Okay, so therefore the transfer, it is going to take place from higher concentration to lower concentration. So that is because of concentration difference. Okay, that transfer is because of concentration difference. So this transfer is your mass transfer. Okay, so it takes place due to concentration difference or even pressure difference, partial pressure difference leads to mass transfer. So all these are driving forces, right? All these are driving forces for some transfer to take place, right? So this driving force is responsible even for energy transfer. Okay, it is responsible even for energy transfer. Okay, so if energy is being transferred from one body to another, it is because of some driving force. Okay, so the form in which energy gets transferred is generally heat or work. Okay, these are the two major forms in which energy gets transferred. Okay, this is the definition according to thermodynamics. Okay, we're not talking about any other definition. We're only restricting our discussions to thermodynamics. So the form in which energy gets transferred in thermodynamics is either heat or in the form of work. We'll discuss how. So when energy transfer takes place due to temperature difference, remember temperature difference over here is the driving force. Okay, temperature difference is the driving force over here. So when energy it is transferred due to temperature difference, then it is known as heat. Okay, then it is known as heat. If the transfer takes place due to some other driving force, then it is known as work. Okay, so these are two very important terms that you need to keep in mind, heat and work. We'll discuss more about these terms now. So when we talk about work done is basically divided into two parts. One kind of a work done is the internal work done. Okay, internal work done is usually due to the change in volume of the system. Okay, change in volume of the system. Okay, so if we talk about work done, then work done is going to be work done on or by the system due to change in volume of the system. So let's say if I have my system, which is initially having volume, let's say V1, and finally its volume changes to V2, then because of this volume change, whatever work is done by or on the system, that is known as the internal work done. Okay, that is known as the internal work done. Okay, and then external work done is basically work done on or by the system due to some shaft or some other external energy. So for example, let's say I have a solution over here and I have a stirrer over here. Okay, this is how a stirrer looks like. So if I have a stirrer over here, this is a motor which is driving the stirrer. Okay, so the stirrer, it is going to rotate, right? And it is going to transfer some of its energy. It would transfer its energy to the solution over here, right? It is going to transfer its energy to the solution over here. So this energy that is transferred, now energy is transferred either as heat or work. Now over here, the driving force is not heat, not temperature difference. The energy is not being transferred because of higher temperature or lower temperature over here. It's not that. It is just externally transferred because of some other driving force. Okay, other than temperature difference, there is some other reason why this energy is being transferred over here. So therefore, it is categorized as work, right? And since this work is not caused, not done because of change in volume of the system, therefore, this is categorized as external work done. Okay, this is categorized as external work done. All right, so remember, and whenever we talk about internal work done, it is mathematically given as minus integral PdV. All right, we'll discuss about the sign and all a bit later. Just understand that W is equal to minus integral PdV. Remember that. Okay. Now, let's talk about a very important term, that is internal energy. So internal energy is basically the energy that exists in the system by virtue of translational, vibrational, and rotational motion of molecules in the system. So over here, you can see these molecules. They are moving in this pattern, right? They are moving in this pattern, right? So this movement of molecules is basically giving rise to some energy, right? Because of this motion of these molecules, there is some energy in these molecules, right? We are talking about a system. Let's talk about a liquid, say. So this liquid, it's totally still, but still its molecules, it will keep on moving, right? So these molecules, they'll just have a translational, rotational motion or vibrational motion. So over here, you can see this is translational motion. All right, this is translational motion. Okay, they are moving like this, right? Like this. Some they're moving in straight line paths. All right, so this type of motion is your translational motion. So because of this, there would be some energy that would be present in the molecules. Let's call it ET. ET is heat translation. Okay, translational energy. Then over here, you can see this molecule, it is moving to and fro about its mean position, right? It is moving to and fro about its mean position. This kind of motion is known as oscillatory motion. And when these oscillations are very fast, this kind of motion is known as vibrational motion. Okay, this kind of a motion is known as vibrational motion. So the energy that would be present in this molecule because of vibrational motion is going to be EV. That is vibrational energy. And over here you can see the molecules cannot just they'll not just simply vibrate or translate. There is also a possibility that they might rotate. Okay, they might rotate about their axis, right? So this rotational motion might be something like this, or something like this, right? This rotational motion is going to impart another energy in the molecules, that is ER, rotational energy. So internal energy is basically the sum of all energies present in these molecules. Okay, in these molecules, and then we'll multiply these energies with the number of molecules to get the total energy. This total energy is going to be the internal energy. Okay, so internal energy is basically energy by virtue of translational, vibrational, and rotational motion of molecules in the system. Okay, this kind of an energy is known as internal energy. Then we come to next term, that is heat. So heat, we've already discussed. It is the form of energy which is transferred from one body to another as a result of temperature difference. So if let's say temperature over here is T1 and let's say temperature over here is T2, then heat transfer then the energy transfer is going to take place in the form of heat. Okay, it is going to take place in the form of heat. Again, the unit of all these energies is going to be joule. The SI unit is going to be joules. Okay, so the form of energy which is transferred from one body to another as a result of temperature difference between different bodies, this is known as heat. Okay, it is also referred to as thermal energy. Okay, it is also called thermal energy at times. All right, so that is heat. And finally, we come to a concept called indicator diagrams. So indicator diagrams are also known as PV diagrams, which are very important, very, very important in thermodynamics. Okay. So most of the problems that we'll be solving, we'll have to plot or draw a rough sketch of a PV diagram and then proceed with our problem. So it's quite important. The PV diagrams are very important. So you need to understand the PV diagrams very nicely. Okay, so basically PV diagrams are pressure versus volume diagrams. Okay, they are pressure versus volume diagrams. So over here, pressure is plotted in the y-axis and volume is on the x-axis. And we get something like this, a curve like this. It can be anything, it might be of any shape. It's a very arbitrary shape that I have drawn over here. So it can be anything. It can be in any way. So that kind of a diagram is a PV diagram. All right. So keep these things in mind, these few definitions that we have done so far. Okay. Now we come to another term, that is heat capacity. So you people have just seen that heat transfer takes place due to temperature difference, right? Heat transfer takes place due to temperature difference. So the amount of heat that would be transferred, it is directly proportional to temperature difference. Okay, it is directly proportional to temperature difference. So when we'll remove this proportionality sign, we'll get C, a constant of proportionality, C, which gives us C equals to Q, heat transferred upon delta T. So this can be written as heat transferred per degree rise in temperature, right? So for 1 degree rise in temperature, whatever would be the heat transfer, that would be C. So this quantity is known as heat capacity. Okay, this quantity is known as heat capacity. The unit of heat is joule. The unit of temperature difference or temperature is Kelvin. All right, and also you should keep in mind that delta T, it can be having both degrees Celsius or Kelvin. It's the same thing, because let's say if you have T1 is equal to let's say 10 degrees Celsius and you have T2 is equal to 20 degrees Celsius. So that would give you this as 283 Kelvin, and this would become 293 Kelvin. So when you find delta T, which is T2 minus T1, so that is going to be 10, that is 20 minus 10, or 293 minus 283. It's always, it can be degrees Celsius or it can be Kelvin. There, it doesn't matter. Okay, so these two need to have the same unit. The two temperatures that you are subtracting, they need to have the same unit, either degrees Celsius or Kelvin. But whatever unit they might have, that's fine. Okay, so at times you might also find this as joule per degree Celsius. It's the same thing. Okay, for temperature, wherever you use temperature difference, joule per Kelvin is same as joule per degree Celsius, or Kelvin is same as degree Celsius when you're talking about temperature difference, not absolute temperature, not temperature of a particular object, a particular system. No, only temperature difference. Temperature difference, for a temperature difference, Kelvin and degree Celsius are going to be the same. Okay. Then we come to, on the basis of heat capacity, we come to specific heat capacity. So if you might have remembered, we discussed a concept called specific volume somewhere in the previous few videos. We discussed specific volume. So specific volume is basically volume per unit mass. Similarly, specific heat capacity is going to be heat capacity per unit mass, or it can be said as heat capacity per kg. So the unit is going to be joule per kg Kelvin or joule per kg degree Celsius. Okay. And then molar specific heat capacity, if you remember, we discussed about molar volume. Similarly, molar specific heat capacity is heat capacity per mole. Okay, so joule per mole Kelvin or joule per mole degree Celsius. Same thing. All right. So this is usually CS and this is CM or CSM, right? Although we'll be rarely using these symbols. Okay, we'll all just come to C at the end. Okay, C, CP, CV, all these things. Okay, rarely these symbols are used, but you should know that. Okay, then heat capacity at constant pressure is CP. It is denoted by CP, and heat capacity at constant volume is denoted by CV. Okay, CP and CV. And the ratio of these two, that is heat capacity at constant pressure upon heat capacity at constant volume, the ratio is given by gamma. Gamma. So gamma is a property of various gases, right? So for monomolecular gases or unimolecular gases, it can be different. Sorry, monoatomic gas, it can be different. For diatomic gas, it can be different. For triatomic gases, it's going to be different. So it depends on the number of atoms in a gas molecule. Okay, so for example, if I say oxygen, it is a diatomic gas, right? It has two molecules of two atoms of oxygen in one atom of oxygen, right? And then CO2 is a triatomic gas. So it depends on the number of atoms. Gamma is dependent on the number of atoms. Okay. So that's a concept that comes from the kinetic theory of gases, which we'll not go into too much depth about. So that's all. Then this is something that we are going to have in thermodynamics from now, and it is going to be there with you forever. Okay, so work in is negative. If work is done on the system, then it is going to be negative. Remember that it is going to be negative. Work done on the system is going to be negative. Work done by the system is going to be positive. Okay, work done by the system is going to be positive. Okay, heat that is going out is negative and heat in is positive. Remember. Okay, so if heat is added to the system, it is going to be positive in nature. It is going to be plus, suppose 20 joules is added, so plus 20. And if it is extracted from the system, then it is going to be negative. So remember these concepts. Work in is negative, work out is positive. Heat in is positive, heat out is negative. Okay, this is the basic sign convention that is followed in thermodynamics. All right. Now, with all these concepts that you've learned so far, we come to the first law of thermodynamics. So the first law of thermodynamics is another statement for energy balance, or it is another statement for the law of conservation of energy. Okay, so it implies that heat can neither be created nor be destroyed. It can only be transformed from one form to another. Okay, so energy, law of conservation of energy is basically about energy in general, and first law of thermodynamics makes this energy balance statement specific to heat energy. Okay, so this basically, in simple terms, it gives you that if I have a system, and I'm adding heat to my system, right? I'm adding heat to my system, then in that case, heat added heat added, it is going to be either stored. So energy stored is basically your internal energy, or it is going to be extracted as work. Okay, so it's either going to be stored or it is going to be extracted as work. All right, so this is the statement for first law of thermodynamics. The first law of thermodynamics gives you a specific statement for energy balance. dq, heat added, is equal to du, energy stored, plus dw, work done. Okay, so remember, work out is positive, work in is negative, heat out is negative, and heat in is positive. Okay, so the sign convention always needs to be kept in mind. All right, then we are going to talk about thermodynamic processes, and we are in some way going to apply first law to these thermodynamic processes. Okay, so this thermodynamic processes, for now we'll just be discussing about 4 processes: isobaric, isochoric, isothermal, and adiabatic. We'll discuss about more processes as time passes by, but for now just let's keep our discussion to these 4 processes: isobaric, isochoric, isothermal, and adiabatic. So isobaric process is a constant pressure process. All right, isobaric process is a constant pressure process. So in this case, pressure is going to stay constant. All right, so if we draw a PV diagram for an isobaric process, so since pressure is always constant, therefore the PV diagram would look something like this, or it would look something like this. Okay, this arrow, what is the significance? I'll discuss about this in a few minutes. Okay, so this is something, what is your isobaric process, constant pressure. Then we talk about isochoric process, which is a constant volume process. Okay, so in that case, volume remains constant. In case of a in case of an isochoric process, volume remains constant. So it's going to be something like this. Here, as you can see, volume is constant. Okay, then an isothermal process is basically a constant temperature process. Okay, so a constant temperature process, the PV diagram looks something like this for isothermal process, where constant temperature is maintained. Okay, so temperature here is same as here, everywhere it's going to be the same. And finally, we come to adiabatic process. The PV diagram is also of the same state, same shape. All right, somewhat like this. It would look something like that. We'll discuss about this diagram, the difference in the 2 diagrams, how to identify which one is an adiabatic process and which one is an isothermal process. All right, so we'll discuss about how to differentiate between two processes from a diagram. All right, so from the PV diagram. So we'll discuss about this further. Okay, so these are the 4 different processes: isobaric, which is a constant pressure process; isochoric, which is a constant volume process; isothermal, which is a constant temperature process; and adiabatic, which is a process in which no heat transfer takes place. Okay, so these 4 processes you need to keep in mind. So now let's in detail discuss about thermodynamic processes. Okay, so remember, the most basic definition of a thermodynamic process is that a thermodynamic process, it takes your system from one state to another. Okay, so this one state, let's call it state A, would be your initial state. So the system would be taken from this state to another state, which is your final state. Okay, So thermodynamic process basically is the path traveled by the system to move from this state to this state, from initial to final state. Okay. For an ideal gas, remember PV is equal to nRT. This is an ideal gas equation, right? Now, the most important state variables that are used to define a particular state are pressure, volume, and temperature. So let's say P1, V1, and T1 are the state variables at the initial state, and P2, V2, and T2 are the state variables at the final state. Okay. So if I'm taking my system from initial state to final state, okay, then in that case, you can see over here that PV upon T is basically N into R, right? This is what you can see. So PV by T is going to be constant as long as N is going to be constant. So for constant N, that is constant number of moles, you're going to get P1 V1 by T1 is equal to P2 V2 by T2. This is the general equation of state, general equation of state for an ideal gas. Okay, for an ideal gas. So if it is moving from state A, that is state 1 to state 2, then the three pressure, volume, and temperature can be related in this way. P1 V1 by T1 is equal to P2 V2 by T2. Okay. And the second condition might be that, let's say it is going from its state 1 to its state 2, but in between, let's say at a particular state, state 3, let's say some of the moles have been released or some of the moles have been added, something like that. So number of moles have changed, let's say. So in that case, for variable n, now if you go for a variable n, then this n will also come here. So you'll get PV by NT is equal to R. So basically you will get PV and NT. Oh, sorry, PV by NT is going to be constant. So let's say number of moles here are N1 and number of moles here are N2. So over here you'll get P1 V1 by N1 T1 is equal to P2 V2 by N2 T2. This is the general equation of state for variable number of moles. Okay. For variable number of moles, this is going to be the general equation of state for an ideal gas. So remember that. Okay. So for now, we'll be dealing with constant number of moles only, but further, we'll also deal with variable number of moles. So you need to keep both of them in mind. Okay. So with this, let's start our first process, that is a constant volume process. So constant volume process is also known as an isochoric process. Okay, it is also known as an isochoric process. So in a constant volume process, let's say you are going from P1 V1 T1 to P2 V2 T2. If you're going from this to this, then in that case, you're going to have V1 equal to V2 because it's a constant volume process, right? It is a constant volume process. So therefore, the general equation of state P1 V1 by T1 is equal to P2 V2 by T2 simplifies to P1 by T1 is equal to P2 by T2. Okay, remember, this is my equation of state for a constant volume or an isochoric process. Okay, this is my equation of state for an isochoric process. Okay, then another thing we discussed about work done. Work done is basically integral PdV. We're talking about internal work done, assuming there is no external work done. Okay, we are, for the time being, we are going to assume that no external work done comes into the picture. So one of our assumptions is going to be no external work done. Okay. So internal work done is going to be in minus of integral PdV. Okay, minus integral PdV. Okay, that is your work done, right? So if I draw a PV diagram, right? If I draw a PV diagram, so in general, for work done, in general, you'll have that, let's say if this is my PV diagram for a particular process, right? And it is going from its initial volume V1 to its final volume V2, right? Or from initial, whatever, from, let's say that it is going from this point to this point. So this arrow signifies the direction in which the process is going. So if it is going from here to here, that means this is my initial state and this is my final state. If the arrow is in this direction, then that means this is my initial state and this is my final state. Okay, so that is your basic thing, right? So in that case, yeah, so in that case, when we have initial state to final state, then the work done is going to, first of all, when we talk about magnitude of work done is simply going to be integral PdV from smaller volume. So over here, smaller volume is V1 to larger volume, which is V2. Okay, this is going to be the magnitude of work done. So magnitude of work done is going to be the area under this curve. Okay, area under the curve which is covered by the PV diagram. Now, remember that if it is an expansion process, if it is expansion, so we discussed in the sign convention that work out is positive and work in is negative, right? This is what we discussed. So if it is an expansion process, if it is an expansion process, so that basically means that, let's say this is my system. This is my system and it is expanding, right? It is expanding. So this, if it expands, it is going to exert force in the outward direction, right? If it is expanding, it is going to exert force in the outward direction. And if it exerts force in the outward direction, then it is going to definitely send work out. It is going to send work out, right? So in that case, for an expansion process, this work done is going to be positive of the modulus. All right, positive of the modulus. And for a compression process, for compression, work done is going to be negative of the modulus, because same logic, work done is going to come in. Okay, so in that way you will get the result. Okay, so this is the general procedure. So for now, we'll be deriving all the formulas with respect to this formula. That is, W is equal to minus integral PdV. Okay. So if it is expansion process, that means it is going from smaller volume to larger volume. Okay. It is going from smaller volume to larger volume. And if it is my compression process, then it is going to be larger volume to smaller volume. Okay, so we'll discuss and we'll see the formulas, and then the modulus of work done is going to be we are going to calculate modulus of work done, and we'll be solving problems based on that. Okay, so don't get confused with this formula minus integral PdV. It's usually plus according to the sign that we are the sign convention that we are going to follow. It is plus. I just gave this formula because in certain books you might see it as minus integral PdV, so you might get confused. But once we will solve problems and once we'll discuss about them, we'll be more clear. So I would recommend that instead of using this formula and getting confused about signs, it is better that you use this method. Okay. First of all, find the modulus of work done. And then depending on whether it is a compression process or expansion process, you can decide the sign later. Okay. So for now, we are dealing with a constant volume process. So since it is a constant volume process, therefore, V1 is equal to V2 and there would be no volume change. So dV is going to be equal to 0, right? dV is going to be equal to 0. And if you see the PV diagram for a constant volume process, then the PV diagram looks something like this, right? Something like this. So let's say this is its initial state and this is the final state. Then it is moving from 1 to 2. So I have drawn the arrow like this. So if you see that the area covered by this area under the curve is basically 0, right? The area under the curve 1 to 2, it's 0. So that is why your work done in an isochoric process is 0. Internal work done in an isochoric process is 0. Okay. So if W is 0 or you can say dW is 0, then in that case, we'll say that you have from the first law of thermodynamics, which stated dQ is equal to du plus dW. So since dW is 0, therefore we'll simply have dQ is equal to du. Okay, for an isochoric process, dQ is equal to du. Okay, then we come to the next process. These are easy processes: isochoric, isobaric. So the second process is going to be isobaric process. So isobaric is basically a constant pressure process. So in a constant pressure process, you get P1 is equal to P2, right? This is the general thing about isobaric process. So if that is going to be the case, then simply the equation of state for an isobaric process, P1 V1 by P2 V2, P1 V1 by T1 is equal to P2 V2 by T2. That is going to reduce to V1 by T1 is equal to V2 by T2. The equation of state is going to reduce to V1 by T1 is equal to V2 by T2. That is going to be the equation of state for an isobaric process, right? If we talk about a PV diagram for an isobaric process, then since over here pressure is constant, right? Since over here pressure is constant, therefore we are going to have diagram in this manner, right? So if let's say this is my initial volume V1 and this is my final volume V2, and let's say this is my pressure P1 equals to P2 equals to P, right? Let's say this is my pressure P. So in that case, the work done, as I told you, work done is going to be the area under the curve, right? And let's say it's an expansion process. So W is going to be positive of modulus of work done, right? It is going to be positive of modulus of work done for an expansion process. So how did we come to know that this is an expansion process? It is going from lower volume to higher volume. So it's an expansion process. So work done, I'll instead of just giving you the formula, I'll give you the magnitude. So magnitude of work done is going to be the area, right? So that area is going to be this area of this rectangle. So this is basically V2 minus V1, and this is basically the pressure or P, right? So the area is going to be P into V2 minus V1 or P delta V, okay, where delta V is basically difference in volumes, which is larger volume minus smaller volume. That gives you the modulus. Now again, if it is expansion process, then it is going to be plus of modulus, positive modulus. If it is a compression process, then it is going to be minus modulus. Okay. Then there can be no as such variations about the law of first law of thermodynamics. So we will simply have dq is equal to du plus dw, and dw we can call it as plus pdv. Okay. Now this may be negative, this may be positive. Okay, depending on the type of process, expansion or compression. Okay, so sign depends on expansion or compression. Okay, so once we have this about isobaric process, let's go ahead and talk about the third type of process, which is quite important for now. It is isothermal process. So in an isothermal process, keep this in mind that your temperature is constant. T1 is equal to T2. So the basic equation of state, it reduces to P1 V1 is equal to P2 V2. Very important, and you're going to use it quite often. Okay, quite often. P1 V1 is equal to P2 V2. And in these processes, remember, as I'm saying, P1 by T1 is equal to P2 by T2. That actually means that P by T is constant. Let's call it a constant K. Okay, so P by T is constant. Over here, it is V by T is constant. So over here, we'll have P into V is constant. Okay, so this is my equation of state. This is my equation of state for an isothermal process. Okay, now if you try to see, this is basically the equation of a rectangular hyperbola. Xy is equal to c, the equation of a rectangular hyperbola. So rectangular hyperbola, somewhat it extends both ways. It extends below and above the x-axis. So the basic graph for a rectangular hyperbola is something like this. This is the basic cover. But since we are dealing with physical system, pressure, volume, so volume can never be negative, right? Volume can never be negative. So we are not going to consider this side of the Cartesian plane, right? So we are not going to consider the second and third quadrant. So that is why we'll have only this as the shape of our PV diagram. So this is going to be there. Okay, so this is my isothermal system. So let's say I'm going from state 1 to state 2. So it is going to be like this. Okay, now work done for an modulus of work done is going to be integral PdV from smaller volume to larger volume. Don't think final, initial, nothing like that. Smaller volume to larger volume. All right. So it is going to be integral. In place of P, we can simply write K by V. So it's going to be K by V dV, and from V1 to V2, right? So that is going to be K, K. Integral of dV by V is going to be ln V, and we have to integrate this from V1, smaller volume to larger volume. So it's going to be K ln V2 by V1, and K is basically PV, and by the ideal gas equation, we know that PV is equal to nRT. So we can say that K is equal to nRT. Now over here, since it is a constant temperature process, and we are assuming that N is also constant, so the entire nRT becomes constant, right? So it actually is a valid statement, right? So in simply, we can say my modulus of work done is nRT ln larger volume upon smaller volume. Okay, nRT larger volume upon smaller volume. Okay. And also we know that P1 V1 is equal to P2 V2 for an isothermal process. Therefore, you will get V2 by V1 is equal to P1 by P2. Okay. So nRT ln pressure corresponding to the larger volume. So generally pressure corresponding to the larger volume is smaller, and P2, which is pressure corresponding to the smaller volume. Okay. So it is going to be ln nRT ln P1 by P2. Okay. Sorry, pressure corresponding to the smaller volume upon pressure corresponding to the larger volume. So generally, if your volume occupied is less, then it would have a greater pressure on it. So therefore, even this is going to be positive, right? So this is basically your modulus of work done. Okay. And for an isothermal process, remember temperature is constant. Okay. And for an ideal reversible system, the internal energy only and only depends on temperature. Okay. Internal energy, it only depends on temperature. So if internal energy is, so if temperature is constant, even internal energy is going to be constant. So since U is constant, therefore, we are going to have du equals to 0. Remember, for a constant temperature process, internal energy is always going to be constant. So you'll get du equals to 0. So that gives you dq simply equals to dw. Okay. From the first law. Okay. Now again, the sign, it depends on compression or expansion. If expansion is taking place like here, then work is going to be positive of modulus. And if it is, if compression is taking place, then it's going to be negative of the modulus. All right. Then we come to the fourth process, which is slightly complicated and not simple. All right. So this is adiabatic process. Okay. This is going to be the adiabatic process. So just like we had equation of states over here, there is nothing, if we see the general equation of state, that was this one. Over here, there is nothing, no term that tells you that what happens if heat is constant, right? There is no term that would be able to give you a proper explanation on the fact that if heat is constant, then what we are going to do. So for now, I'm not going to go into the derivation of the equation of states because I have not really introduced any concepts over here. So I'll just tell the equation of state is PV to the power gamma is constant, where gamma, if you remember, gamma, we have discussed it as Cp by Cv, ratio of heat capacity at constant pressure and heat capacity at constant volume. Okay, so that is gamma, which is Cp by Cv. Okay. So this is my equation of state for an adiabatic process. Remember, PV to the power gamma is equal to constant. Okay. And from here we can is equal to constant, which is K, of course. And from here we can say P1 V1 to the power gamma is equal to P2 V2 to the power gamma. Okay. Also, since in general, since the general equation of state gives you P1 V1 by T1 is equal to P2 V2 by T2. So using this equation of state, you can actually find the relation between pressure and temperature as well. So for example, V1, this can be written as P1 into V1 by V2 to the power gamma is equal to P2. And from here, you can write V1 by V2 as P2 by T2 into P1, into T1 by P1, right? So over here, you can write P1 in place of V1 by V2, you're going to write P2 to the power gamma into T1 to the power gamma upon P1 to the power gamma into T to the power gamma is equal to P2. So when you simplify, you'll get P1 to the power gamma minus 1 upon T1 to the power gamma is equal to P2 to the power gamma minus 1 upon T2 to the power gamma. Okay, this is, if I'll simplify this a bit more, so you'll get P1 to the power gamma minus 1 by gamma whole by T1 is equal to P2 to the power gamma minus 1 by gamma upon T2. So both these equations you can keep in mind. This is slightly easier to remember, while this is a bit simplified version of this as well. All right, so this is how you can relate pressure and temperature, and similarly you can relate temperature and volume. Okay, you can simply substitute in place of pressure, you can substitute in place of P1 by P2, you can substitute T1 by T2 into V2 by V2. So that way you will get the equation as T1 V1 to the power gamma minus 1 is equal to T2 V2 to the power gamma minus 1. So this way you can use your equation of state to calculate any of the, suppose if they have given you P1 V1 and P2, so you can calculate V2. If they have given you P1 T1, then you can calculate P1 T1 and T2, then you can calculate P2 and so on, right? So this is basically the application of equation of state. Once we will be solving a few problems, you will get more hold of it, right? Then work done by an adiabatic process. So again, the PV diagram for an adiabatic process, it somewhat looks like an isothermal process only, something like this only, but it's there's slight difference between the diagrams of PV PV diagram for an adiabatic process and PV diagram for an isothermal process. There's slight difference between the two diagrams, so we'll come to that. Okay, for now you can keep this in mind. All right, so now when we find work done, so modulus of work done is basically integral P dV from V1 to V2, right? And P can be written as K upon V to the power gamma. So you will have from V1 to V2 K dV upon V to the power gamma, right? So this, when you integrate this, you get K upon V to the power gamma minus 1 into 1 upon 1 minus gamma, right? Into, and this you have to integrate from V2 to V1 to V2. Okay, so you will get this as K upon gamma minus 1 upon V1 to the power gamma minus 1 minus 1 upon V2 to the power gamma minus 1. I have taken this minus outside. So I have, in place of 1 minus gamma, I have taken gamma minus 1. Therefore, we have got 1 upon V1 to the power gamma minus 1. Okay. So when we simplify this, and then in place of K, we can write P1 V1 to the power gamma over here. And over here, we can write P2 V2 to the power gamma. So we will simply have P1 V1 minus P2 V2 upon gamma minus 1. That is the general formula for work done. P1 V1 minus P2 V2 upon gamma minus 1. And in place of P1 V1, we can also write it as NR T1 minus T2 upon gamma minus 1. So this is the general formula for the adiabatic process. okay, for work done in an adiabatic process. And since in an adiabatic process, you don't have heat transfer, so dq is equal to 0, that gives you du is equal to dw in an adiabatic process. Okay, so once again, I'm going to give a general brief about the 4 thermodynamic processes that we have dealt with. The first thermodynamic process that we have dealt with is, okay, process, equation of state, magnitude of work done, and finally first law, how we have applied the first law to it. So the first process that we dealt with was an isochoric process. So an isochoric process in which you have volume constant. Okay, volume is constant. So if volume is constant, therefore the equation of state, it becomes P by T is constant, which when applied can be written as P1 by T1 is equal to P2 by T2. Okay, magnitude of work done for an isochoric process is going to be 0. Therefore, application of first law gives you dq equals to d. Okay. The second is isobaric process. In that you have pressure constant. So the equation of state becomes V1 by T1 is equal to V2 by T2, or simply V by T equals to K. The work done is given as magnitude of work done is basically P times V2 minus V1, where V2 is the larger volume and V1 is the smaller volume. This is the magnitude of work done. Okay. And over here, you'll simply get dq is equal to du plus dw. Not much variation in the first law. Then the third process that we studied was the isothermal process. So that has temperature constant. So the equation of state becomes P1 by P1 V1 is equal to P2 V2, or PV is equal to K. Right, that becomes the equation of state. Work done in an isothermal process is equal to nRT ln larger volume by smaller volume, which can also be written as nRT ln the larger pressure by smaller pressure. Okay, and over here du is 0, so you will get dq is equal to dw. Okay, and finally you have the adiabatic process. You have the adiabatic process. So in adiabatic process, there is no heat transfer, so dq is equal to 0. So in that case, the equation of state of an adiabatic process is P1 V1 to the power gamma is equal to P2 V2 to the power gamma. Okay, this can also be written in terms of pressure and temperature and volume and temperature. Okay, this equation of state can be written in terms of all the three variables. Okay, work done in case of an adiabatic process is P1 V1 minus P2 V2 upon gamma minus 1, which is nR T1 minus T2 upon gamma minus 1. And since there is no heat transfer, so du would be equal to dw. Okay, so these are the 4 important processes that we studied in thermodynamics. So far, we have studied these 4 important processes. So you can pause the video, note it down, or people might want to take a screenshot of this. But this is very important, and we are going to use this quite a lot. So please keep these formulas, these specifications in mind before we continue further.